So, welcome back to this class on hardware security. So, we shall be continuing our discussions on microarchitectural attacks, and we shall be today studying an attack which is called as Rowhammer attacks, which is essentially a new class of microarchitectural attacks which targets the DRAM. So, like we have seen like previous attacks which targets the SRAM or the cache memory, but this actually targets the DRAM which is present in our modern day processors. So, the concepts that I will be covering are, first we will take a look at the DRAM organization. We shall be trying to develop an idea of row hammers. Then we shall be trying to study the address mappings, like the various address mappings from the virtual address to the physical address, and also like from the virtual address to the cache memory, like how essentially we kind of access the cache sets and corresponding slices in the cache. And finally, we shall take a look at the attack and also discuss a potential countermeasure which is essentially popular against Rowhammer attacks. So, to start with, here is a look at the DRAM organization. So, this is a very simplified view of how the DRAM looks like. So, you can see that the common form of the DRAM chip essentially has got several components, and the components can be studied in this following or it is organized in this following fashion. So, on one hand you have got the DIMM. So, the DIMM essentially is shown by this green bar. So, this stands for the dual inline memory module, and this typically comprises of several ranks of memory. So, for example, here it has been shown that there are two ranks, and each of these ranks in turn corresponds of like several cells of the DRAM memories, which are essentially called as banks, and therefore, the row comprises of several banks. For example, here there are 8 banks shown, and if you look into each of these banks, then it is basically a regular organization of cells of DRAM memories, and each of these essentially are or can be realized potentially by a one transistor implementation, where there is one transistor and there is one accompanying capacitor which basically stores the content of that specific cell. So, the DRAM essentially is a regular organization which essentially comprises of these components, that means the cells, the banks, the rows, and the DIMM, and finally the channel which basically connects it with the memory controller. So, the idea is that what we will be studying in this particular attack is essentially or basically originates from understanding the physics inside of what happens in your bank in your DRAM memory. So, for example, each of these, if you go into the bank of the memory, then we will see that the DRAM cells are organized as rows and columns. It is a regular organization of rows and columns, and there is one access transistor. So, this is the transistor which basically kind of stores or essentially it enables to write and also read data from the cell, and you can see that there is a capacitor which basically stores the content of the specific cell. Now, this access transistor is connected to a word line. So, this is your word line. Okay, so which when on connects the capacitor to the bit line. Okay, so this bit line, so basically you can read or write the corresponding data through a row buffer. So, there is also an accompanying row buffer. So, the idea is that when this specific word line and bit line gets connected, then this particular transistor or the corresponding capacitor basically gets connected to the row buffer. So, the content of the entire row essentially is deposited into the row buffer, and therefore, we can read the content from the row buffer. So, reading or writing is done through a row buffer which can hold charge for the entire row. Therefore, the entire row, if I for example want to access the row 2, then the content of row 2 is stored in the row buffer. So, the row buffer serves as something like a cache of your content. That means, like next time when you are accessing again the row 2, then you do not need to go and access row 2, but you can get that content quite fast from the row buffer. So, that essentially improves the overall performance of the DRAM cell, of the DRAM memory. On the other hand, if you are reading from another row, for example from row 1, then you essentially have to kind of evict that data from the row buffer, and you have to basically put the data from row 1 to row buffer and then read the content from row buffer. Okay. So, there is something like a conflict which can happen in the row buffer. So, typically there are 3 steps when you are accessing this. So, there is an opening row, that means you basically enable the row, you read or write to the cells, and then you close the row. So, these are like the 3 broad steps that would take place. So, as we know that in a one transistor model or in this kind of DRAM cells, the charge in the cells will decay with time, and therefore, this needs periodical refresh. Otherwise, right, the content of the data gets essentially tampered, and that would potentially lead to errors or faults inside your DRAM cells. So, typically the refresh period that we use is 64 milliseconds. That means every 64 milliseconds there is a refresh cycle which happens to kind of like refresh the states of the corresponding cells. So what is row hammer? So row hammer is essentially a bug or like an exploit which has been found in the modern day DRAM chips, and it essentially stems from the fact that row hammer is a term which is coined for the disturbances in the recent DRAM chips which repeated row activation causes. So therefore, if you are repeatedly activating the rows, then a specific kind of errors occur which are called as row hammers or row hammer errors. So this activation or repeated row activation causes the DRAM cells to electrically interact with each other, and this repeated discharging and recharging of the cells of a row results in leakage of charge in the adjacent rows. So if repeated enough times, typically before the automatic refresh, because as we have seen that the refresh happens only in 64 milliseconds. So if you are accessing this faster than that, then this repeated accesses can cause potential flipping of bits in the adjacent rows, and this essentially is termed as the row hammer or essentially the row hammer bug. So this instrument of doing the repeated access is essentially called a row hammer, and we will see like how that can be used as a potential instrument to create faults in targeted secrets which are located somewhere in our DRAM cells. So what is the underlying principle, or let us see how we can perform hammering by seeing a very high level code for doing this operation. So here is a regular arrangement of the cells arranged in rows and columns, and this is the corresponding row buffer. So what we are trying to do here is basically we are trying to make a regular access to these components, and we essentially the objective is that we would like to create a fault inside one of the rows. So what we basically try to do is shown here by this code snippet. So we can see here we are trying to use this, for example, these two move instructions essentially are trying to read from address X and read from access Y. So the idea is that when you are reading from access X and when you are reading from Y, so you are basically wanting to read from the content of X and Y. So note that one thing that we will always keep in mind throughout our discussion on the attack is that the address, when we are accessing a specific memory location, then that content could be there in your potential cache memory. So therefore, if you really want to kind of understand or observe the phenomenon, what happens in your actual DRAM cell, we have to ensure that that data is not available in the cache. So we have to kind of evict the data from the cache. So we can use dedicated instruction shown here, which is like CL flush, which essentially evicts the data from all levels of the cache. For example, when we do a CL flush X, then that data is not present in the cache. Similarly, if I do the CL flush Y, then also that data is not available in the cache. So these two things basically ensures that next time when I am accessing the data from the address locations X and Y, then I am indeed accessing the DRAM cells and not the cache memory. So when I am accessing, for example, these two rows like X and Y, so these are two different addresses, and imagine that they get mapped into two different rows in a specific bank of the DRAM, then the data would be, so initially when I am accessing, for example, this row, then say the I-1th row, then the content basically comes from the row buffer, and therefore the next time if I access the same row, then I get the data from row buffer. So in order to create the flip, we basically, as we know, that we have to basically ensure that every time I have to access the corresponding row in the bank and not the row buffer. So therefore I need to ensure that I basically make the next access, say maybe at address Y, which is at a different row in the corresponding bank. So therefore, if this two accesses, for example, the access to X and the access to Y happens very fast, kind of faster than its refresh cycle, then the adjacent row, as shown here as the ith row, shows or may show certain bit flips. For example, a 1 can potentially get 0, and that essentially would mean that there is suddenly a fault which happens in your adjacent row. So we have seen that faults essentially can be quite catastrophic to cryptographic implementations and also in general security, and therefore flipping bits in memory without really accessing them is really a serious threat that we need to consider. So therefore, right, I mean, of course, like modern day DRAM cells comes with several levels of protection, but we can see that in certain scenarios we are able to create such kind of bit flips, and therefore it seems like this instrument of row hammer is a quite powerful tool, and we can potentially apply it with the objective to create bit flips in cryptographic keys which are stored in memory. Of course, like it would not be easy, but it seems like we can potentially try to do that, and that is something that we would like to study subsequently. So we have an instrument like the row hammer, and we would like to apply it, and we would like to study first of all what are the challenges and objectives of like this instrument that we have found. So the first thing we observe is that the secret is residing in some location in the cache memory, and also in some unknown location in the main memory, kind of something that I do not know, because I do not have handle exactly on where it is, where it is located and where it gets mapped into the actual DRAM memory or even the cache memory. So the attacker, having user level privileges in the system, does not have the knowledge of these locations even the last level cache. So we will considering the last level cache, because typically it is shared by several cores, and apparently this makes the attack much more conducive. So we will be considering the LLC cache and the DRAM, since these locations are decided by mappings of the physical address bits. So as an attacker, I do not have knowledge about or direct knowledge about the corresponding physical address bits, from which I can understand like the corresponding locations in the DRAM or even in the LLC. So in order to perform the row hammer on the secret exponent, the adversary first needs to identify the corresponding bank in DRAM in which the secret exponent resides. That is the first objective that we have. And along with it, if the adversary frequently queries the decryption oracle, that means like for example, we will be assuming a threat model where the adversary is kind of interacting with your target, basically is allowing the target or the victim to perform decryption with his secret key. Okay. So the idea is that if the adversary frequently queries the decryption oracle with valid ciphertext, decryption process will perform exponentiation with which will basically make an access to the secret exponent, and that is what we want as an attacker. We want that the attacker again and again performs decryption with the same key, and we would basically in that process or during that time try to understand where that secret is located in the DRAM cell and also even in the LLC cache. So, but access requests, as I said, right, are usually addressed from the cache memory, because again and again if you allow the like the process to the victim to execute on the same content, then the data would be available in the cache memory, and therefore we would not be able to observe this phenomenon and exploit it. So therefore what we do is basically make an access. We basically adversary incorporates a spy which runs concurrently to the target process, and then uses the timing side channels, something as we have already seen previously in context when we discussed about cache attacks, what is called as prime and probe attacks. And we basically kind of employ a prime and probe attack to understand the mapping into a channel, rank, bank where the secret has been correspondingly mapped to. We also would like to kind of use this spy to ensure that the data is always evicted from the cache. That means we basically want to know the corresponding mapping of the secret exponent into the last level cache, so that even the spy right is making an access, I mean the victim basically is always making an access to the actual DRAM cell and not to the cache memory. So this is a like a very simple organization of cache memory, a very standard organization of the cache memory. So for example, consider in our system we will be considering a 4-core architecture. So we know that we have got private L1 caches, we have got L2 caches, and then there is a unified L3 cache that is essentially serving as the last level cache. So the idea is that in recent processors there is a hierarchy of cache memories. The size of each cache level increases as we move higher. So you can see that the size progressively increases, and the last level cache is shared across processor cores, and it takes larger time and is further divided into slices for concurrent access by cores. So targeting the last level cache is therefore conducive because it is shared by several cores, and the effect is more observable. So what we can observe here is that the first thing is, therefore, we have to understand the address mappings, like from the virtual address to the physical address. So let us take a quick look back to our architecture textbooks. So here is a virtual address mapping, so which is essentially divided into two parts. One is the page offset and the other part is a page number. And then the memory management unit basically kind of has got a mechanism of giving us the frame number and the page offset, which is basically combined to get the corresponding physical address. However, when you are accessing the cache memory for a 4-core machine, we will be essentially having 4 slices in the cache. The idea is that the mapping from the physical address to the corresponding location in the, so basically like this is an M-way set associative cache. So in our particular architecture, we will be considering a 12-way set associative cache, that is the experimental setup that we will be considering, but in general it is an M-way set associative cache, and these are all the 4 potential slices. So each slice essentially has got several sets, and every set, so imagine that suppose there are C sets for example, and each of these sets essentially has got M ways. Okay, so therefore potentially, right, we can have M ways for every slice, and there are C potential sets. So these are my corresponding C sets, and there are M ways in which the mapping can occur. So therefore, right, I mean, you can observe that there is a hash function, and we will kind of elaborate about that subsequently. This essentially has been unfurled in some of the research papers, and essentially potentially gives us a reverse engineering on this mapping, because this may not be exactly documented in the available white papers. So there are some prior research which basically tells us how this mapping takes place, and as we can see that the set index here basically tells us what is the corresponding set index, but there are M ways. So there are any of the M ways are potentially possible, and where this particular address maps, for example the corresponding slice where it maps to is indicated by this hash function, which takes a 30-bit input and generates a 2-bit output, which is used to index any of the 4 potential slices. So this is the corresponding mapping that we would like to understand and decipher as much as necessary. So therefore, right, with this background, let us take a look at the corresponding attack strategy. So the first job, right, is basically to ensure that when the target or the victim basically executes on your unknown secret exponent, then every time it is accessing the secret exponent, it is basically making an access to the DRAM and not to the cache. So we have to evict it, and because of that, right, we have to understand the eviction set. We have to understand the corresponding eviction set, that means the footprint of the secret exponent on the cache memory. In order to understand that, we will basically apply a technique which is called as prime and probe, and that is something that we have already studied previously. So the idea is that the adversary is oblivious of the virtual address space, which is used by the decryption engine, and thus involves a spy process to do that. So the adversary basically kind of uses a spy, and the spy essentially so basically this spy process basically uses or employs this prime and probe cache access methodology to identify the target sets. So the idea is basically the spy primes a corresponding area in the cache memory and subsequently comes back after the execution of the victim and probes its own accesses. If the individual access time takes a significantly large amount of time, then it basically kind of assumes or guesses that those areas has been evicted by the victim process, and that is why it is taking more time. And with that, right, it basically understands this mapping and understands eventually the eviction set, which is essentially required to ensure that, or this understanding is important to ensure that every time the secret exponent is kind of accessed subsequently when we actually launch the attack, the access should be done from the DRAM and not from the SRAM or the cache memory. So the idea here is that the spy process targets the last level cache, as we have discussed, since it is shared with all cores of the system. The spy initially allocates a set of data with elements and consults its own page map to obtain the corresponding physical addresses for each element. So in this attack, right, we are basically assuming that the spy essentially has got a user level access to the page map, and with that essentially it can know its own physical addresses. Okay. However, it must be kept in mind that because of these potential attacks subsequent to Linux kernel version 4, this access to page map has been made restricted. However, there may be like several systems where still these are enabled, and more importantly, right, in embedded processors, right, we may still have access to this kind of page maps at user levels, and which could be potentially a security threat. Moreover, right, there could be other ways of circumventing this, but at least, right, for this within the scope of this course, we will be restricting and assuming an access to page map. That means the spy, right, can understand the corresponding physical addresses of its own access patterns. So, for example, if it makes a memory map, then it knows the corresponding physical address of the accesses which it is making itself. So here is essentially a like a quick look about like a document from www.kernel.org, which basically tells that since Linux 4.0, if you are accessing this without the root privilege, then you would not get the page map access, and the reason is the information about this is restricted because this has been exploited in Rowhammer vulnerabilities, and therefore this is a serious threat to be considered. So here is the basic broad strategy behind the attack. So the cache set collision with the secret. So we basically want to kind of understand the eviction set, and we can understand this in a step by step process which is illustrated in this diagram. So the adversary basically initiates the spy process, and the spy process basically generates a memory map. So it does a memory map and it computes the set slice addressing from its physical address. So as I said that it knows its corresponding physical addresses by using maybe page map. And for the target set T, so for example, it basically fixes the target set T. So the target set T, as we have already seen, can be found out from its physical address. And right, I mean, for every target set C, set T, there are m possible ways, okay, because it's an m way set associative cache. So it selects m elements in distinct cache lines which maps to a set T for all the k possible slices, because there are k slices, that is what we are assuming, and it primes the LLC by accessing these selected elements. So basically primes means it kind of fills up the cache memory with these potential locations, and then it basically sends a selected input to the decryption engine and allows the target or the victim to decrypt. So note that if when the corresponding cipher text is returned back to the adversary, because the adversary is also interacting with the decryption engine, and that is quite a practical threat model, because any adversary can access or can interact with a secret or with essentially a decryption engine, and when it receives the decryption or decrypted message from the decryption engine, it basically asks the spy to get or to start probing, because it has already done the priming operation. Now it will basically start probing. So the probing means the spy will access the selected elements again, and for every access will measure its time. The idea is that if this time is more than a threshold, then it will basically kind of conjecture or assume is that the decryption engine probably has come and evicted those things, and that is why I am taking more time, and through that it basically understands the footprint, and from there the eviction set for the decryption exponent. So note that one thing should be kept in mind, that this mapping from the virtual address to the corresponding physical address can change every time. So therefore, right, what we are studying right now is a methodology, but that does not mean we can, when we again start or restart this process, the mapping will be the same. So therefore, we have to do, as we will see later on, when we do the attack, we have to do the attack all at once. We have to do the attack in situ. Okay. But this basically tells us how the mapping can be deciphered, and this basically we will use as subsequently as an oracle in my broader attack, which we will discuss subsequent to this. So this basically kind of tells us about the reverse engineering of the cache slice selection. If the target system is having k processor cores, then the LLC has got k slices, as we have already seen. Each slice has got c cache sets, and each set being m way associative, or there is an m way associativity. So, that means that if the cache line size is of b bytes, like if the cache size is of b bytes, so for example 64 bytes, then we will be using the least significant log 64 base 2 or log b base 2 bits of the physical address as an index within the cache line. And again we will be for getting the set number, we will be using log c base 2 to indicate or determine the cache set number. And because of associativity, m such cache lines having identical log c base 2 bits reside in the same set. Now, we already discussed about the hash function, which basically is already like established in these two prior papers, which tells about how to perform the reverse engineering to know or obtain the corresponding slice number from the physical address. So, with this reverse engineering in mind, what we do is to precisely control the eviction of existing cache lines from the set T. The spy runs a selection algorithm to select an eviction set of m into k elements belonging to each set T. Then the selection algorithm, so basically selects elements of distinct cache lines for each of the k cache slices such that the physical addresses maps to the same set T. In addition, each set of a slice is m-way associative, and therefore, the selection algorithm selects m elements corresponding to each k cache slice belonging to the set T. The spy accesses each of these m into k selected memory elements repeatedly to ensure that the cache replacement policy has evicted the existing cache lines. Okay. So, the idea is that right now, if you basically observe, then you are in a scenario where you have basically been, so if you basically target a specific set, there are m possible ways over here, right. So, this essentially is a specific slice of the cache, suppose the slice I for example, there are m possible ways, okay, and there are k such slices. So, suppose there are k slices. So, therefore, if you kind of understand or fix the corresponding set, then totally there are mk possible addresses or m into k possible addresses. There are m ways per slice and there are k slices. So, totally there are mk possible addresses. Okay. So, these are the for every target set T, therefore, the spy basically runs a selection algorithm and therefore, it basically probes these mk selected memory elements and tries to understand which set corresponds to the secret exponent. So, the idea is that it basically will probe for all the corresponding C sets that are there. So, remember that there are potentially C sets that we are considering, and for every set there will be mk possible locations. So, it will basically probe these locations and try to understand which set among these C sets are corresponding to the secret exponent. Okay. So, this essentially implies that with this setting, what we essentially can do right now is we can basically launch the prime and probe analysis. So, the spy basically primes the target set T, so that is your specific target set T out of the C possible sets and becomes idle. So, prime means it basically fills up the cache with those mk possible addresses. The adversary sends the chosen ciphertext for decryption and waits till the decryption engine sends back the corresponding message after decrypting. So, note that the objective of the attacker is not to get the message, but to get the secret exponent, because that is more important. If cache sets used by the decryption is same as the spy, then the cache line primed by the spy process gets evicted during the decryption, and the adversary signals the spy now to start probing. So, it basically starts to probe at those mk locations, and the spy process accesses each of the selected m elements of the eviction set T for all the k slices, and the time to access each of these elements are observed. When the spy again accesses the same elements, if it takes longer time to access, then we conclude that the cache set has been accessed by the decryption and therefore it takes more time. So, one can try to make this attack more interesting and can try to go into the slice also, because remember that we also have an understanding about how the slice has been selected, and we will see subsequent to this, right, that how we can make the attack even more concentrated or more focused by getting into the slice, where we can reduce the possible sets or eviction set from m into k to only m values, because now we basically are considering only a specific slice. So, for illustrating this attack, we will be basically considering in our subsequent class on a 1024 bit RSA implementation, which is essentially using square and multiply as the underlying exponential algorithm using GNU MP big integer library, and this is the corresponding version. And the experiments will be illustrated on Intel Core i5 processor, which has got an Intel Ivy Bridge microarchitecture, which is running an Ubuntu 12.04 LTS with a kernel version of 3.2. Note that here we can essentially get unrestricted page map. Okay. And the Linux, as I already mentioned, the Linux kernel version for our experimental setup being older than version 4.0, we do not require administrator privileges to perform the entire attack, but the exact description of the attack we will see in the next class. Thanks for your attention.